All right. Hey, y'all. So we're going to jump into section 4.4, which is all about zeros of polynomials. So zeros of polynomials are x values that make that polynomial equal 0. So let me give you a quick example up here. So if I've got x squared minus 2x minus 15, and I wanted to find the zeros of this, basically it just means what are the x values that are going to make this function value or the y value equal 0. So we would just solve for x by factoring and getting the zeros. So zeros are directly related to factors of a polynomial. So if we factored this, we would get something that multiplies to negative 15, adds to negative 2. So that's going to be negative 5 and 3. So we can factor this. So I have my factors, and if x minus 5 is a factor, then positive 5 is a 0. If x plus 3 is a factor, then negative 3 is a 0. So I'm just emphasizing the relationship between a polynomial's factors and their zeros. If we know their factors, we can quickly find their zeros. But likewise, if I know their zeros, if x equals negative 3 is a 0, I can work backwards and say, well, that must mean x plus 3 is a factor. So we'll come back to that in a little bit. So first we'll start with the factor theorem, and that says that for all polynomials p of x, x minus c is a factor of p of x if and only if c is a 0. So in other words, if p of c equals 0. And I'll relate that up to this, back up to this example I did here. If x minus 5 is a factor, so x minus c is a factor, then p of c, so p of 5 has to equal 0. So because x minus 5 is a factor, if I plugged in 5 to my polynomial, it would be 0 times 8, which is 0. So it's just another way of reiterating information we already know. So if x minus c is a factor, then p of c equals 0. That is, x minus c is a factor if and only if c is a 0 of p of x. So use the factor theorem to show that x minus 1 is a factor of x to the 6th minus 1. Well, here's my factor. So what would the 0 be? It would be 1. So using the factor theorem, I just want to evaluate this at 1. 1 to the 6th minus 1 equals 0. Again, if x minus 1 is a 0, then 1, plugging 1 in, should give me the value 0. Same thing with number 2, use the factor theorem to show that 3x minus 2 is a factor of this polynomial. The tricky thing here is that 3x minus 2 is not in the form of x minus c. But if 3x minus 2 is a factor of this polynomial, so let's think about 3x minus 2. Could I rewrite that so that it is in the form of x plus or minus a number? Couldn't we just factor out the 3? So that would be x minus, and when I factor 3 out of negative 2, it would just be 2/3. So if this 3x minus 2 is a factor, then 3 times x minus 2/3 is also a factor. So this, we would use the 0 that we got from this, which is 2/3, to plug in here using the factor theorem. So using the factor theorem would mean to evaluate this whole function at 2/3. So that means we would type into our calculator 3 times 2/3 to the 4th plus 4 times 2/3 cubed minus 19 times 2/3 squared plus 7 times 2/3 plus 2. So if we evaluated this in our calculator, which I'm not going to do right now because I'm short on time, I would get 0. And that verifies that 3x minus 2 is a factor. Okay, so now again, this all seems like kind of straightforward stuff that we've already talked about before, but it's just reiterating the relationship between a factor and a 0, or a polynomial's 0 and its factor. So if x minus 6 is a factor of some polynomial p of x, what x value is a solution of p of x, really this should say, is a solution of p of x equals 0. Basically, if x minus 6 is a factor, what x value is going to make p of x equals 0? And that would be the 0 of 6. Okay, so now we're going to talk about using a polynomial's zeros to factor it completely. So up until this point, we've done a lot of different factoring strategies. This polynomial right now is not a quadratic, so I can't use the factoring strategies for quadratics. I can't use factoring by grouping or chunking because I don't have any common factors in each group. We just don't have a strategy for this. So when we're factoring polynomials that we don't know a strategy for, we can use any zeros from the graph. So we can use zeros from the graph to build the factors. So the first thing we would do in this example, trying to make it so the glare is not so bad here. How can I do that? There we go. Okay. So I've already typed this in. So I've got, is this the, yeah, 6x cubed minus 17x squared minus 31x plus 12. I've got that in my calculator here. If I take a look at the graph of this, here's its graph. Sorry, I'm a little unfocused. It's focusing on my paper, not the calculator. Okay. If you look at the zeros here, it's not going through an integer, but it looks at these two zeros. But it looks like it is at 4, and I'll come back to that. But first, let's talk about the number of real zeros. Real zeros are instances of x where the function actually touches the x-axis. So this has 1, 2, 3 real zeros. The next question is saying find one integral zero. So basically that means find a zero that's an integer. Integral means find a number that's an integer, that's a 0 from the graph, or using the table. It looks like on here that it's crossing the x-axis at 4. So if I hit trace 4, I can just confirm that. So I plugged in 4. I really wish this would focus. I'm sorry, it's not. Ooh, okay, so I traced at 4. I get the y value of 0. So I do have this one integral 0 of 4. So 4 is a 0 of this polynomial. But since I know 4 is a 0, then let's think about what must be a factor of this polynomial. I'm going to refer back to this example here. We're used to looking at factors and then using those factors to tell what the zeros are. But going backwards, if 5 is a 0, then x minus 5 must be a factor. And it's literally just the algebra. Subtract 5 from both sides, and then you have x minus 5 equals 0. So there's your factor. So that means down here, if 4 is a 0, that means x minus 4 has to be a factor. And why is that helpful to us? Well, our goal, what we're trying to do is factor this polynomial. So if I can use the graph to find 1, 0, which means I've found one factor, I can divide this factor out of my polynomial to continue factoring the entire thing. So basically what we want to do is divide our polynomial 6x cubed minus 17x squared minus 31x plus 12. I want to divide that whole thing by x minus 4, and we just learned how to do polynomial division with long division or synthetic division. So luckily this is in the form of x minus c, so we can use synthetic division here. So we're going to set up our synthetic division. My c value is 4, so I'm going to write 4 up here in the left-hand corner in a little box. Then we list out all of the coefficients in descending order of our dividend. So that would be 6 for my x cubed term, negative 17, negative 31, and 12. Then we continue with this synthetic division. So remember, we draw a line, leave a little bit of space to write numbers in the next row, and we bring down our first term, which is 6. 6 times 4 is 24. We write that in the next blank under negative 17. Then we combine negative 17 plus 4, or 24, which is the same as 24 minus 17, which is 7. Then we repeat, 7 times 4 is 28. Put that under the negative 31. Combine negative 31 and positive 28, we get negative 3. I know that this last number here is going to be my remainder. We finish with negative 3 times 4, which is negative 12, and 12 minus 12 is 0. We should absolutely expect that to be 0. Why should the remainder be 0? That's because we know for sure that x minus 4 is a factor. We know for sure going into it that that should happen. So if we know that x minus 4 is a factor and we get a remainder other than 0, that's a red flag that we've made a mistake here in the synthetic division process. Okay, so remember our main goal was to factor p of x. So right now, we first discovered that x minus 4 is a factor. And when I divide that out, I get this quotient right here using synthetic division. So p of x is x minus 4 times 6x squared plus 7x minus 3. So I've started factoring it, but I can continue factoring p of x. Now that I've factored out this linear factor and I'm left with a quadratic, now I can factor this quadratic because we know how to do that. So I will factor my quadratic down here. So 6 times negative 3 is negative 18. 7 here. Well, it multiplies to negative 18 and adds to 7. That would be 9 minus 2. And then since my leading coefficient was not 1, we're going to need an area model as well. So I've got 6x squared negative 3, 9x minus 2x. And then, so since something's going to be multiplying to 9 and 6, that's going to be my side with 3x, and this will be my side with 2x. So 3x times 3, and then 2x times negative 1. Okay, I know I'm going through this a little bit quickly. Slow down the video if you need to, pause, rewind, whatever you need to do. So now I've just factored this quadratic, and now I've got the final factor form of p of x. So we've got x minus 4 times the way my quadratic factors, so 2x plus 3, and 3x minus 1. So using the graph, just a recap here, we used the graph, identified one 0 that was an integer, which gives us one easy factor, x minus 4, which we know is a factor, so we can divide it out, which we did with synthetic division. Took that result and rewrote our polynomial in a semi-factored form, and then factored the remaining quadratic, and now we've got it completely factored. Completely factored means we should be able to list out all the zeros. So listing all the zeros, if x minus 4 is a factor, then 4 is a 0. If 2x plus 3 is a factor, then just set that equal to 0 and solve. We get negative 3/2. And same with 3x minus 1. If we set that equal to 0, add 1, divide by 3, we get positive 1/3. So we've got all of our zeros here after we used the graph to factor it completely. Okay, so we'll do a couple more of those examples in a few minutes. I'm gonna run through something called the rational roots theorem. So the rational roots theorem is a theorem that allows you to figure out all of the possible rational roots of a polynomial. Rational, so let's recap what rational is. It's basically a fraction of an integer divided by an integer. So I will write that down. An integer divided by an integer. And to figure out what those possible rational roots are, we need to pay attention to our leading coefficient in front of the highest x power and the final constant, which is the coefficient of x to the 0th, basically. So it's the constant. And if we're talking about these two numbers, so the C is going to represent the set of all of the factors of this constant. So C is the set of factors of A sub 0, which is just that last constant. So constant term. And D is the set of all of the factors of the leading coefficient. I'm just going to write A sub n, leading coefficient. Okay, so if we can list out all of the factors of this constant and list out all the factors of this leading coefficient, then all the combinations of C divided by D are going to give us all of our possible rational roots or zeros of a polynomial. I just want to reiterate that roots are zeros. So roots are zeros, zeros are roots interchangeably. So C, again, factors of the constant. D are all of the numbers that are factors of leading coefficient. And I'll show you a quick example to make sense. Okay, so how do I use the rational roots theorem? So looking at number 5, you find all possible rational roots of P of X. So this would mean I'm going to try and figure out what are all my possible roots without looking at a graph. So first we would want to list out all of the factors. So -4, this is that constant at the end. So that's that set of C, which is basically all my possible numerators for all possible roots. So factors of -4. So we'll list out the set of all of the factors of -4. Well, let's start with the basics. 1, but also -1. So basically it's always going to be positive and negative of whatever the factor is. So positive and -1 are factors of 4. Positive and -2 are factors of 4. And then finally positive and -4 are factors of 4. So now I need all of my factors of my leading coefficient, which would be 3. Factors of 3. So the whole set of factors of 3. Well, 3 is prime, so it's only 2 factors, or 1 in itself. So we've got positive and -1 are factors, and positive and -3. So now it's time to use that rational roots theorem to list out all possible. These are just possible, not all of them. But if there are any rational roots of P of X, they're going to be in the list we're about to make. Possible roots of P of X. So all of those roots are going to come from all ways that we can write a fraction of these numbers divided by these numbers. So I just do this systematically. So the possible numerator of 1 divided by positive or -1. That gives me a possible root of 1/1, which is 1. So I've done that. And then also 1 divided by 3. So that would give me another possible rational root of 1/3. So those are the only options with 1 in the numerator. Then I would move on to 2. 2/1 or 2/3. So we've got positive or -2, positive or -2 divided by 3. And then lastly, I've got positive or -4/1, which is just positive or -4, and positive or -4/3. So if P of X has any rational roots, they will have to be in this list. These are the only possible rational roots. So why is this helpful? If we had no calculator, no graphing calculator, and we couldn't check to look at the zeros on the graph, we could just check. I can check and see if any of these are zeros simply by plugging them in. So I can plug in +1, and if it equals 0, I have found a 0 or -1, plug it in and see. We're not going to walk through that whole process. I just wanted to introduce this theorem to you and show you how we can find all of the possible rational roots of a polynomial. Okay, so let's do another example or two here. So this is fine, saying to divide the polynomials, then continue factoring completely. So basically the goal is to factor this, and I'm basically telling you x plus 2 is one of its factors. So if x plus 2 is a factor, continue factoring the entire thing. Well, if I know x plus 2 is a factor, then I can divide it out. Thankfully, this is linear, so I can use synthetic division. So I would just take my c value of -2, put it up in a box, list out all of my coefficients of my polynomial. So 4, -12, -19, and 42. Continue on with the synthetic division. So we bring 4 down. 4 times -2 is -8. Combine -8, -12, we get -20. -20 times -2, 40. Combine 40 and -19, that's positive 21. Multiply 21 times -2, -42, which means my remainder is 0. Again, if I don't get 0 as a remainder when I'm for sure positive that x plus 2 is a factor, that's a red flag that something has gone wrong. You should absolutely expect the remainder to be 0 if we know something is a factor. Okay, so what we've done now is partially factored our original. We factored it down to x plus 2 times this quadratic result, 4x squared minus 20x plus 21. And then I just need to continue factoring by factoring this quadratic. So this one, again, we're told to factor, so we can assume we're going to factor here. So I can use my diamond. 4 times 21 is 84, -20 down here. Okay, this one took me a second trying to find my two numbers that multiplied to 84 and add to 20. Or -20, because I wanted it to be 20 and 1 really badly. It did not work. So with a little bit of trial and error, guessing and checking, you would hopefully come to the conclusion that you've got two numbers, 6 and 14 multiply to 84. So if I want those to add to -20, -6 and -14 would have a positive product and add to -20. Then I would just use my area model. And 4x squared down here, 21, -6x, -14x. All right, and now we've got, I'm going to have to do 2 and 2. So 2x and 2x to get my 4x squared, -3 to get -6x, and -7 to get -14x. All right, so now I can write my final factor form, which would be x plus 2 times 2x minus 3 times 2x minus 7. So now we have the final factored form because we were given one factor. And now we've got this, whoops, factoring to that. Okay, so I'm going to stop for now because, like I said, I'm short on time. You'll find the second half of these notes in the next video where we'll finish up relating a graph to its factored form of the polynomial, which is one of my favorite things. So you guys will see that on the next video. Okie dokie. See you next time.